In topic 1.1, we introduced the idea of concavity, concave up and concave down functions. In section 1.2, we introduced the idea of computing rates of changes for functions. But now we're going to tune it in and make average rate of change very particular for linear and quadratic functions. Now we know from previous courses a linear function looks like a straight line. Yes? Okay. For any linear function, the average rate of change over any length input value interval is constant, which is why it makes this same shape. When you answered questions in Algebra 1 about a linear function, you were like, what's the slope? And you're like, 4. Rise 4, run 1. You did that the whole time. Meaning that the average rate of change has a changing rate of 0. It doesn't change. It's the same the whole time. Okay. However, when we start to look at curvy functions, specifically a quadratic function with its parabola shape, for any quadratic function, the average rate of change over consecutive equal length input value intervals can be given by a linear function, meaning the average rate of change changes at a constant rate. So let me make this make sense for you. Remember when we did average rate of change, we considered average rate of change to be the slope of the secant line. So if I were to draw a secant line between these 2 points right here, my secant line would look like this. And if I took the same amount of interval going the other direction, continuing on this graph, it would have a different rate of change. I totally missed that dot there. However, if we take the same amount of changes each time and use the same interval around and around this parabola over and over again, those would have a constant change in the number. So let's see what this looks like when we get to a table, because sometimes it's easier to see this in a table and then apply it back to a graph. The table in example 1 shows given values of the function f of x. We're going to explain why f of x is not a linear function based on the average rates of changes. Okay? If we notice here, we don't have consecutive lengthed intervals. Don't write this down, just watch for a second. The difference between 1 and 2 is 1, between 2 and 4 is 2, and between 4 and 8 is 4. So we don't have consecutive length input value intervals. However, what we can do is compute the average rate of change for each of these things. The average rate of change is the slope of the secant line between these 2 points, which means we would put the outputs over the inputs. 7 minus 4 over 2 minus 1. Let's use our brain for this one as some brain work. What is 7 minus 4? 3, 2 minus 1. So my slope here is 3. Let's find the average rate of change between the next 2 points. Outputs over inputs. So I would do 10 minus 7 over 4 minus 2. What's 10 minus 7? 3, and then 4 minus 2? Ooh, is that the same number I got when I computed the rate of change just a second ago? 3 over 1 and then 3 over 2. Okay, so we don't have the same rate of change. Let's see what happens when we do one more. We do 13 minus 10 and 8 minus 4. 13 minus 10 is 3, and 8 minus 4 is 4. So again, my average rate of change over these open length or any intervaled length input value intervals is not the same. So our conclusion is the following. F of x is not a linear function because over any interval given, an interval of 1, an interval of 2, and an interval of 4, the average rate of change is not constant. And if the average rate of change is not the same number, we don't have a linear function. So let's make a note for ourselves. The average rate of change must be the same on a linear function. And since we didn't have the same number going all the way down for my average rate of change, it is not a linear function. So in example 2, it's going to make us work kind of hard for this, but let's consider now a quadratic function, just the parent function x squared. We're going to complete the table of values for x squared, then use the table of values to compute the average rate of change over and over again and draw our conclusion. So this is my function we're using right now. This is just g of x equal to x squared. So that means for each time I get a new input value, I'm going to plug it in and get an output value. When the input value is -3, we plug it in right here. What is -3 squared? 9. We take -1, plug it in, because it's an input value. What's the output value? 1. When I plug in the input value 1, what's the output value? When I plug in 3, what do I get out? And when I plug in 5, what do I get out? 25. Okay, that's the classic parent function. If we were plotting these points, we'd have these coordinates, -3, 9, -1, 1, and on and on. Now it's asking me to find the intervals for these average rates of changes. Remember, the intervals, these are input values. So we want to make sure we're using those as my input value on these intervals to create the average rate of change. To show my work here, I'm going to zoom in because my handwriting is too big. But what we're going to do is put the outputs on the top and the inputs on the bottom. The output at -1 is 1, and the output at -3 is 9. I don't know what word I was trying to say here. Over -1 minus -3. If you're like, Miss Quigley, where are you getting these numbers from? Remember, average rate of change for this problem would be g of x2 minus g of x1 all over x2 minus x1, where the outputs are what we got from the g of x side of the table, and the inputs are from the input side of the table. Well, if we're showing our work, 1 minus 9 is -8, and 1 minus -3, minus a negative means to do what? Add, so it's really just -2 plus 3, that's 2, which means my average rate of change is -4. Okay, let's do one more together, and then I'll have you fill out the rest of this table yourself. So we have average rate of change again between -1 and 1, so I'm using these numbers this time. The output at 1 is 0, the output at -1 is not 0. Wow, what am I doing? The output is 1. If we compute this, this is 0 over 2. What is 0 over 2? 0. Let's just practice one more time doing our average rates of changes. I want you guys to fill out the rest of this table. So this next row is asking you to find the average rate of change between 3 and 1, and the last row between 5 and 3. Okay, I know I might not have given you enough time to really do that all the way through, but hopefully you got a little practice. What was happening here again is we are taking this interval, these are the input values, grabbing their associated output values and subtracting them on top. When we do this, though, when we compute this average rate of change, my first question for us is always going to be, is my average rate of change the same number over and over again? No, so it's definitely not a linear function. We know that it's quadratic because those are all different. However, look at the change in this rate of change. If we were to go from -4 to 0, how would we do that? And from 0 to 4? And from 4 to 8? In a previous class, you would have called this the second differences. So if our second differences are the same, that means the change in our rate of change is the same. And if the change in your rate of change, second differences, is the same, then we have a quadratic function. Here's our conclusion sentence we could write. The average rate of change of g of x over what's called consecutive equal length input value intervals, and let's break down what that means. Consecutive means one after another. Equal length meaning they're equal intervals, and I'm talking about this from -3 to -1 plus 2 plus 2 plus 2 plus 2. Those are consecutive equal length, so in a row, equal length input value intervals. Okay, but let's talk about the average rate of change. We found that the average rate of change here, these numbers in your table, are not constant. Instead, they are changing at a constant rate of 4. They being the average rate of change. Therefore, the rates of change of the quadratic function are given by a linear function because we have a constant change or constant slope in our average rate of change. Now this concept seems kind of wild, but if we get into some actual practice questions and the kinds of responses I'm looking for you, this is like more definition style. On the back of your notes are more like the kinds of questions you're going to see. And before we say, I don't get it yet, let's just do a couple more to make sure we don't get it. In example 3, we have 3 tables. For each table, we're going to determine if the function could be linear, quadratic, or neither, and we're going to give a reason for our answer. Okay, if we look at the very first thing here, what we want to do is compute the average rate of change for each of these intervals. So we're going to practice that average rate of change formula over and over and over again. Can I show y'all a quick shortcut to make sure we always line these things up right? Y'all watch the board for a second. Here's my division bar, right? I'm going to put the bottom input value minus the top input value down first. Right? So here's the bottom input value, here's the top. Then I'm going to go back over it, I'm going to line up the correct output value above it. So 2 and 1 go together. 0 and 1 go together in a column, yes? Then we can compute. 1 minus 0 is 1, 2 minus 1 is 1, so my first average rate of change is 1. Fabulous. If we find this average rate of change again, the bottom input value for this middle grouping is 3. So we'll do 3 minus 2 on the bottom and 4 minus 1 on the top. Inputs on bottom, outputs on top. 4 minus 1 is 3, 3 minus 2 is 1, so my average rate of change for that interval is 3. If I do that for the last one, this is going to be 4 minus 3 and 9 minus 4, which is 5 over 1, which gives me 5. So the first part of our question here is what kind of function would it be potentially? Linear, quadratic, or neither? It's linear when these numbers you compute are all the same. So are they all the same? No, it's definitely not linear. It is quadratic when these numbers we computed all change with a pattern. How do you go from 1 to 3? How do you go from 3 to 5? 2. Oh, snap. So is this change the same? If the change in the rate of change is the same, that means that this is a quadratic function. And the reason, again, we're going to write it down. The function could be quadratic because the average rate of change changes at a constant rate, and that rate is +2. Now I'm going to be very, very picky for a second, and I'm going to give you a look behind the curtain. I typed the words average rate of change on here. On your homework, I don't think I typed the words average rate of change in your description, which means what words will you make sure you write in your explanation each time? Average rate of change. On your quiz, then when I quiz you over this one, I will not write the average rate of change. What should you put in your response? Because if you just say it, wrong. I don't know what you're talking about if you just refer to something as an it. You're talking about the graph, the outputs, the average rate of change. We have to talk exactly what we mean. So we are saying that this function could be quadratic because the average rate of change changes at a constant rate. We make sure we say all of that. Can we try one more before I give you one to try on your own? Okay, fabulous. If we're computing the average rates of change again on this interval, again, the trick is second input minus first input first, and then just line up the coordinates as they go. 1 minus 0 is 1, 2 minus 1 is 1, so that first value is 1. Hooray. The second interval, between 2 and 5, so I put a 5 minus 2 on the bottom, line up the 4 and the 5, line up the 2 and the 1. 4 minus 1 is 3, and 5 minus 2 is 3. Oh, snap. That reduces to 1 again. This would be 10 minus 5 on the bottom, 9 minus 4 in my numerator. 9 minus 4 is 5, and 10 minus 5 is 5. And again, we get 1. Okay, we got 1 as my average rate of change for each individual average rate of change we got. What does that mean for us? This function could be linear. And the reason is because the average rate of change is always what number? 1. We would say because the average rate of change is constant. It is the number 1. It never changes from that. And if you have a constant rate of change, that's the definition of a linear function, because the average rate of change is constant. Okay, this last one is for you to try. 3 little average rate of change problems, and then draw a conclusion. Did y'all get the following average rates of change? 1, and then 1/2, and then 0. First easiest answer is this function going to be linear? No, because they weren't all the same number. Easy. Eliminate those answer choices if there were answer choices. The next question is, would this be quadratic? No. Let's check. Because if we go from 1 to 1/2, how did I change? 0.5. Minus 1/2, right? How did I go from 1/2 to 0? Didn't I minus 1/2 again? So the change in our rate of change is actually the same. If the change in our rate of change is the same, what does that mean for our function? That means that our function is probably quadratic, because that second difference, or the change in the rate of change, is all the same. So we're going to say the function could be quadratic because the average rate of change changes at a constant. Wow, can I make my handwriting any worse? Let's try that again. Constant rate, and that constant rate is subtracting by 1/2. If there was not a pattern between your average rates of changes, like let's say one was +5 and one was -3, then you would say neither. Okay, that's when you would say neither. But we do want to look for that pattern in the rates of changes to see if it changes at that constant rate. Now, we started to talk about this before, but let's pull back the idea of concavity from the first lesson. We remember from the first lesson that concave up portions of graphs are portions of the graphs that look like our hands when we put our wrists together and fingers up. So this section right here, this entire parabola, this happy parabola, is concave up. In the second example, the concave down, the sad parabola, concave down. We get concave down graphs when our fingers are touching but not our wrists. But what does that mean for the average rates of change? Okay, for concave up function, the average rate of change over equal length input value intervals is going to be increasing for all small length intervals. Concave down, however, means that the average rate of change over equal length plus u input value intervals is decreasing for all small length intervals. Notice I'm not talking about the function, I'm talking about the rate of change. When we start talking about the function increasing and decreasing, that's when we're talking about going up and going down. So this side of this parabola, would you say is increasing or decreasing as a function? decreasing. So what we can describe this as, and this is kind of trippy, we can describe this section of the parabola that it is decreasing at an increasing rate. Whoa. That portion of the graph is decreasing, going down, negative slope, but the slope itself is increasing. So the function is decreasing, the slope is increasing because of concavity. So how do you think we would describe the other half of this parabola? When it turns on that turning point and goes up like this, how would we change that description? Would it still be decreasing on that side? But would it still be moving at an increasing rate? Yes. Yes, so how would we change that description? Yeah, this part is increasing at an increasing rate. It's kind of crazy. So remember, the rates increasing and decreasing comes from concavity. The function increasing and decreasing comes from the slopes of the secant lines created by intervals on that side. Let's do the same thing over here. Okay, so we have decreasing at an increasing rate, increasing at an increasing rate. How would we maybe describe the first side of this parabola? This is decreasing? This section is an increasing function, but since it's concave down, that means the rate is decreasing. So the description here would be increasing at a decreasing rate. And then we turn the corner from the top of that hill and we come back down. So we would have described this section the other day as increasing or decreasing function. Decreasing function. So if we put this description together, how would we describe the whole thing? Decreasing at a decreasing rate. So now we know a lot of information about the function in regards to its outputs, increasing, decreasing function, and its rates of change, increasing and decreasing rates of change for concavity. And if we go back to the idea we had from earlier of finding the average rates of change to categorize the functions as quadratic and linear, we can also furthermore categorize these functions as potentially concave up, concave down, or neither. Because now we know that the average rate of change, the way that it's changing, tells me whether it's concave up or concave down. So for example, and we're going to go a little bit faster through these just for time's sake. Do you notice that these are all the same input values? 1 and then 1.1 and then 1.2 and then 1.3. What's the difference between these input values each time? How much am I adding? 0.1. So I would have consecutive, so not skipping around, equal length 0.1 input value intervals. Which means, for sake of time, when you see that you have consecutive equal length input value intervals, when you're doing your average rate of change, you just have to find the difference between these numbers. So what is the difference between 4 and 1? 3, and it's down, right? How about between 1 and negative 1? Down 2. How about between negative 1 and negative 2? Down 1 more, right? Okay, that would be my rate of change because over consecutive equal length input value intervals, that's the change in the function. What is the change in the rate of change? +1 and +1. So since this is a positive number and my average rate of change is increasing every time by 1, that's an increasing rate. So what we learn from this is the function could be concave up. Are y'all okay with that shorthand for concave up? When you're writing out descriptions, eventually we're going to write the whole words out, but for brevity, CCU for concave up. This function could be concave up because the average rate is increasing. We got a positive number as the change in my rate of change. Let's do the same thing for the middle table. Again, we have consecutive equal length input value intervals. They go up by 0.1 each time, so we can fast forward through this part. This is plus 3, and then what? Plus 3, and then what? Okay, your spidey senses should be going off. What kind of function is this? If it's all the same. Linear would be all the same. But let's look at this change in the rate of change, okay? It's all plus 0, right? If there is no change in the rate of change, first of all, we know the function's linear, which means it's neither concave up or concave down because there's no change in the rate of change. This is a straight line. Linear functions have no concavity to them. So this function could be neither concave up nor concave down because that average rate of change is constant. And then just because we know this, aka this is a linear function. Last one, and we'll still do this one together. If I was finding the change in the outputs here, which would give me my rate of change, because we have consecutive equal length input value intervals, how do I go from 1 to 7? And then 7 to 11? And then from 11 to 3. What? 13. 2. Interesting. So it's definitely not linear. Great. How about the change in my rate of change? -2 and -2, right? So we know this is quadratic because we have a constant second difference or a constant change in the rate of change. But is this going to be concave up or concave down? Concave down, why? Because the average rate of change is negative. The change in the average rate of change is negative. So we think that this graph is going to be concave down because the average rate of change is decreasing each time. We have a negative number showing me the change in the rate of change. It sounds like I'm using a lot of the same words to describe different things. I hear it. There is a difference in the way we're talking about the change in the rate of change being constant versus a function being constant. And that's the biggest difference between linear and quadratics that we have to peel apart in our brain. That linear functions have a constant rate of change, and that quadratic functions have a constant change in their rate of change. Yes, I know. Correct.